Just imagine a world that's transforming right in front of our eyes. We're talking about robots flawlessly navigating complex environments, self-driving cars reading the road in real time, medical AI predicting health outcomes before symptoms even show up, and recommendation systems that somehow just know exactly what you want to watch before you do. We are living in a cinematic, truly futuristic reality right now, and it is all powered by one revolutionary concept. Welcome to This Explainer. Today, we're laying out a definitive roadmap, Machine Learning Explained, taking you all the way from a complete beginner to advanced engineering.
It's a pretty profound question, right? Think about it. What if we simply didn't have to write thousands of lines of explicit code for every single scenario a computer might ever encounter? What if the computer could just figure it out on its own? Okay, let's dive into this, because this single idea is literally the engine behind the absolute most significant technological shift of our generation.
So here is our roadmap for today. We're going to start by defining what ML actually is and walk through its workflow. Then we'll explore the different types and core algorithms, check out some real-world applications and the challenges engineers face, and finally wrap up with exactly how to advance your own ML career.
Section 1. What is machine learning? From rules to data-driven decisions. We really need to nail down what exactly we mean when we say a machine is learning.
So, according to Coursera's 2026 roadmap, machine learning is a highly specialized branch of artificial intelligence. Basically, instead of a human sitting there manually programming every single rule, we build algorithms that learn directly from the data itself. And here's the best part. As they ingest more and more data, they automatically improve their performance through experience. They literally get better over time without us touching the code. And this brilliantly illustrates the fundamental shift. In traditional programming, humans input the rules and the data, and the computer just spits out the answers. But in machine learning, we flip that entire concept on its head. We feed the computer the raw data along with the correct answers, the outcomes we're looking for, and the computer outputs the rules. It figures out all the hidden patterns completely on its own.
Section 2. The machine learning workflow. The pipeline from raw data to production. Now that we know what it is, let's look at the actual step-by-step mechanics of how this pipeline operates in practice.
Building a model isn't just about throwing fancy math at a wall and seeing what sticks. It is a rigorous, structured workflow. First, we collect and clean our raw data. Then we do feature engineering, which is basically how we highlight the most important signals hidden in that data. Next comes the actual model training, followed by some serious, rigorous testing, and finally, deployment out into the real world. A really great piece of advice here comes straight from Google's rules of machine learning. Keep the first model simple and get the infrastructure right. Seriously, don't try to build a massive neural network on day one. Get your pipeline flowing first.
Section 3. Types of machine learning. How models learn. We've got our data flowing, but how exactly do we teach the algorithm? Let's explore the different paradigms.
The two absolute heavyweights here are supervised and unsupervised learning. As highlighted by Databricks, supervised learning is all about precision. You use labeled data, think millions of emails explicitly marked as spam or not spam, to predict known outcomes. Unsupervised learning, on the flip side, is for pure exploration. You throw a massive amount of unlabeled data at the model, and it discovers hidden structures on its own. It's like grouping customers with similar buying habits without you ever telling it what those groups should be.
But you know, this field is evolving incredibly fast. Now, we increasingly see semi-supervised learning, which leverages just a tiny bit of labeled data alongside a massive pool of cheap unlabeled data to get the absolute best of both worlds. And then there's reinforcement learning. This is where an AI agent learns to make optimal decisions through pure trial and error, earning rewards for good actions and taking penalties for bad ones. This is exactly how we train those unbeatable game-playing AIs and advanced autonomous robots.
Section 4. Core algorithms and models, the math behind the magic. Stepping into the intermediate phase of our roadmap here, let's pull back the curtain and look at the actual math powering these systems. Now, what's really interesting about this slide is how we specifically match these mathematical algorithms to different real-world problem domains. If you want to forecast continuous values, like predicting house prices, you're going to use linear regression. Need highly interpretable decisions, you'd probably use an ensemble of decision trees, like a random forest. Support vector machines are fantastic for complex classification tasks. And when you finally step into deep learning with neural networks, well, that's when you can tackle high-dimensional data, like facial recognition or complex natural language processing. But hey, before we get entirely obsessed with complex algorithms, we need to pause and really look at this quote from Martin Zinkovich at Google. Most of the gains come from great features, not great machine learning algorithms. This is a massive reality check for any engineer. Human intuition, domain knowledge, and the way you carefully prepare and engineer your data features, that will almost always trump just throwing a fancier algorithm at bad data. Section 5. Real-world applications and challenges. ML in action and in production. Let's step out of the theoretical for a minute. How do these models actually perform in the wild? The impact is literally everywhere you look. Machine learning is instantly detecting fraudulent credit card transactions. It's actively reading genomic sequences to personalize healthcare treatments. It's the hidden brain behind the recommendation engines on YouTube and Netflix, keeping us completely hooked. It's the core of the autonomous systems steering self-driving cars, and the natural language processing that lets you just casually talk to the voice assistant sitting on your kitchen counter. But let's be real, it is far from perfect. Engineers face massive challenges every single day. Models can just memorize training data instead of actually learning from it. That's called overfitting. You also run into immense computational limitations and super high costs. But looking at the technical hurdles, so the crucial point is what experts call training serving skew. This happens when your model performs absolutely perfectly in the lab during training, but then fails silently in the live production environment because the real-world data has subtly shifted. Monitoring for these silent failures is a huge part of an ML engineer's daily job. Section 6. Advancing your ML career. Building a standout portfolio. If you want to be the engineer out there solving those exact challenges in 2026 and beyond, how do you actually stand out? Here's the truth. Hiring managers don't just want to see that you can train a basic model on your laptop. They want to see production-ready skills. Let's move to and see how this builds into a true MLOps workflow, based on insights from AI engineer Mary Nova. You might start by ingesting massive data using Google Cloud Platform. Then you process and clean it at scale with Apache Spark. Next, you train a cutting-edge model using Hugging Face transformers. But you aren't done yet. You then containerize that model using Docker, basically packaging it up so it can run anywhere, and finally serve it to the world through a REST API. This end-to-end pipeline, this is exactly what gets you hired. When you're putting together that portfolio, focus heavily on demonstrating real business value. Don't just list generic accuracy scores, track domain-specific metrics. Like, use the Rouge score to evaluate how well your AI summarizes text. Show that you prioritized feature engineering and explainability over just picking the biggest, most complex architecture. If you can actually design a custom loss function, which is the mathematical formula that tells your model exactly what its end goal is, and align that perfectly with a core business goal, all wrapped in solid MLOps practices, you are going to stand out from the crowd for sure. And as we look to the horizon of 2026, the whole landscape is shifting. Self-supervised pre-training, where models learn from vast amounts of raw data without any human labels, is completely dominating the creation of foundational models. Large language models are evolving at breakneck speed, and vector embeddings are rapidly becoming the core infrastructure that powers enterprise search, retrieval, and reasoning. The field is moving incredibly fast, and it is thrilling. At its core, machine learning is simply teaching computers to learn from data, make intelligent decisions, and continuously improve on their own. It is no longer just shaping technology. It is actively reshaping humanity's future across absolutely every industry. The real question is, how will you use these tools to build that future? Thank you so much for exploring this explainer with me. Make sure to subscribe for more deep dives into the incredible technology that's powering tomorrow.